Division of Mechanics. Let's start today's session. So when it comes to situations where there is conservation of linear momentum as well as conservation of angular momentum, we were discussing, conservation of mechanical energy. We were discussing some questions like that last time, especially the spring mass system type of situations where conservation of both the things applies. So let's look at some examples of that next. Okay. So we have a situation like this on a smooth frictionless surface. We have a combination of two blocks like this, which are connected by a spring, like the problem we were seeing last time. But there's going to be a third block now. So let's say we have this situation. So given that mass of A is equal to mass of B is equal to, let us say, 6 kilograms. Mass of C is double, it is 12 kgs. Okay. And the spring has a spring constant of, let us say, 40 newtons per centimeter. Okay. Now, initially A and B are at rest. And the spring is relaxed. Okay. C has a velocity B naught equal to, let us say, 20 centimeters per second, okay, or we'll make it 24 centimeters per second. Okay. Head on towards A. Now the collision occurs between them, and let's say we are given some coefficient of restitution. So the head-on collision between A and C has a coefficient of restitution equal to 0.75. So we want to find the maximum compression of the spring after impact. Okay. We want to find the maximum extension of the spring also after impact. Okay, so this bit of like a trick question. Okay. Then we want to find B's maximum speed, okay, after impact. So you have to be a little bit careful where you can apply conservation of energy, where you cannot, okay, because there are a number of things happening here. First, C is colliding with A, then A is transferring some of its energy into the spring is delivering some impulse on B. Okay, so A and B together with the spring is acting like a system. So all those things are there. Okay. And of course, through this, we will cover the application of one-dimensional head-on collisions. Okay. So if you're not remembering the formula for 1D head-on collisions, just take a quick look at it. You know, that M1, M2, U1, U2, that kind of formula with coefficient of restitution. Okay, so this is a very standard type of JEE Advanced type of question. Yes, Ganesh, I've just seen your message. We will do that EMI question. Okay. Did you try it with the explanation I had sent you? Like, or you didn't get the time yet? Okay, no problem. I'll do it now. Just read through the explanation once possible. Okay. Anyway, I'll explain the question. It's a good question for everybody to do also. So, okay. Okay, so start working on this now. For the benefit of those of you might be wanting to revise the formula for for head-on collisions. The formula are like this: that if mass m1 has the initial velocity u1 directly towards m2, and m2 has a velocity u2 away from this, okay, then after impact, if we assume that m1 continues but with a slower velocity v1, v1 might become negative also. In that case, it will recoil, okay, like this. So then we have the equations. First of all, conservation of momentum, m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. And then we have the relation that separation velocity is equal to e times approach velocity. So that gives us another linear equation, that v2 minus v1 is equal to e times u1 minus u2. So you can always get by with these equations if you don't remember the direct formula. However, there is always advantage in remembering the direct formula that you get by solving these two. So you should remember this formula. It helps you reduce the amount of time you're spending in solving questions. So solving these equations, we get the very important formula that V1 is equal to M1 minus EM2 upon M1 plus M2 times U1 plus plus M2 into 1 plus E upon M1 plus M2 U2, and similarly V2 is equal to M1 into 1 plus E upon M1 plus M2. Okay. So by now you should be familiar with the type of symmetry there is that you can use to memorize these formulae, and also the various special cases of these formulae, which will help you apply them very quickly. Okay. So for example, in this question, you can see there are many special cases. Okay. If you have E equal to 1 and M1 equal to M2, then you have a very interesting case that they exchange the velocities. V1 becomes U2 and V2 becomes equal to U1. So there is exchange of velocities. You have the case of E equal to 0. You can see that V1 is equal to V2, which is equal to M1 U1 plus, that is the total momentum, divided by the combined mass. So that's one good way to quickly visualize these equations. Okay. Anyhow, so you can make use of these equations directly here, because the first thing you have to understand is that the collision between A and C is not affected by the spring. Okay, I'm repeating this: the collision between A and C will not be affected by the spring, because the collision is a very fast event. So the collision, the impact impulse acts in such a short time that the spring has no time to react. The spring will not compress while the interaction between A and C is happening. So the collision between A and C is over, A starts moving, and then the spring starts compressing. Now we have to treat it like that. Okay, so Aditya, Nishit, because Ganesh, I have one question of yours also. I've received some questions from you. And Jatin, I have received a couple of questions from you also. So I'm going to be discussing some of these questions. Samik, I have received questions from you also. Okay, Bhumik, there's a question from you also about rotational mechanics. So very good. We're going to be concentrating on rotational mechanics and collisions today. So, okay, so all right, Samik, I've received your answer for the first one. So just to save time, I'm going to start working this out quickly. Okay. So the block C, it is moving with a velocity v0. And if you notice in comparison, it has mass 2m compared to E, which is at rest. Okay. So after the collision is over, immediately after the collision is over, okay, if we assume C is having some velocity v1, A will be having some velocity v2. Okay. Just after impact, B will still be at rest. Okay. And the spring will still be at the natural length. So between this and this, what has happened? There is a collision with E equal to 0.75, okay, between A of mass 2m and C. Sorry, between C of mass 2m, right, and A, which is of mass m. So how can we get V2? V2 is the more important thing for us. V1 we don't really require. So V2 will be m1, that is 2m, into 1 plus E, which is 0.75 upon m1 plus m2, so that is 2m plus m, into u1, which is v0, plus something into u2, which is 0. Okay, so you can see that this will become 2 by 3 into 1 plus 3 by 4, 0.75 I can write like this, okay, into v0. So that is becoming 7 by 6 v0. Okay, so 7 by 6 into 24 centimeters per second. Okay, so that should make it 28 centimeters per second. Right, Samik, hope you have got the same value. Okay, so this is just after impact. Now we know from our previous knowledge that when the spring reaches maximum compression, what about A and B? We were just discussing in this last few lectures all these things, that when the spring reaches maximum compression, then at that point of time, the relative velocity between A and B will be 0. So they will have common velocity. Okay, so between this state and this state, so for A plus B plus spring as a system, okay, x is equal to x maximum when velocity of A with respect to B is 0. So let us say VA is equal to VB equal to V. Now they are equal masses, so the V will obviously be half of this. So M into V plus M into V should be equal to M into V2, which was the initial velocity before this. Okay. So we have V is equal to V2 by 2. So in fact, in terms of V0, you can see it will become 7 V0 by 12, or it will become 14 centimeters per second. Okay. So now we can see that. So this was one equation. Okay. And x is equal to x max means that half mv square plus half mv square plus half k into x maximum square. This will be the initial energy. So this is, sorry, v2 square. Okay. So we can now write this like this: mv square plus half kx maximum square is equal to half m v2 square. Now we can express everything like this, that m into, now v, remember, was 7 by 12 v0 square plus half kx maximum square is half m into v2, which was 7 by 6 v0 whole square. No? So this will be an easy way to solve this, that half kx maximum square is equal to m v0 square if we take common. And from here we have 49 by 36 into 2, 72, minus from here we have 49 by 144. Okay. So we have x maximum will be V naught into square root of 2m by k into this factor of 49 by 144. Correct? Hoping this is correct. So this should be 7m by 12. Sorry, 7 V naught by 12 into square root of 2m by k. Okay, and now I'll substitute the values. So after substituting the values, I might get something little awkward, but okay. And I'll have to substitute in SI units so that I get X maximum in, I can substitute V naught in centimeters per second. That's fine. So I'll substitute this V naught in centimeters per second so that I'll get X maximum in centimeters. But these should be substituted in, so this was 6 kgs, I think, if I remember. Yeah, 6 kgs and K was 40 newtons per centimeter. So 6 divided by 40 into 100. So further this will become 14 into, or 14 by 10 into square root of 3 by 10, right? 0.3 in centimeters. So 1.4 square root 0.3, whatever that comes out to be in centimeters. This is what I'm getting as X maximum. Okay, but I mean, more importantly is the parametric part, where I've got it in terms of parametric thing as this. I've got X maximum as 7 V naught by 12 square root of 2m by k. And I substituted m as 6 kgs, k as V naught as 24 centimeters per second. Yeah, Samik, you got the same thing. This is only 7 square root of, if I take this 10 inside, I mean, if I take the 5 inside, so you get 7 by 5 root 6. I'm not sure, something going wrong. Okay, just check your calculation once, because you know these things are all about calculation at the end of the day. I'm sure all of you will get the concepts correct, but you have to. And whatever is the maximum compression, that will be the maximum extension also. Okay, so Samik, it's working out now, the calculation now. Okay. So it's quite a, you know, this thing value 0.3 square root will be about 0.5. So into, I mean 0.54, something like that, into 1.4. So we'll get this as approximately 0.77 centimeters, like this. Okay, now as you know, the maximum compression will also correspond to the maximum extension. So what is happening is initially this one is moving with V2, and this is at natural length, and this one is at rest. Now at this point of time, you can see that the spring length is decreasing. It's compressing till it reaches a stage where both of them have common velocity and the spring has maximum compression. Okay, because they have common velocity. So this has maximum compression. Okay. So from here to here, what is happening? Always in between, from this position to this position, VA is greater than VB. So the spring is compressing. Okay. Now after this, what happens? B picks up more speed than E. So now in the next part of the journey from here to here, VB becomes greater than VA. So the spring starts relaxing. And then it eventually reaches a stage where, okay, now it reaches that stage where at some point of time, B will have its maximum value. So we'll come to what that is. Okay, but that is the stage where this will be back to natural length. X will be 0. And that point of time, VA will have something. Okay. Now after this, what happens? The spring starts extending. Now the spring is extending. So as the spring is extending, so up to here, what was happening? B was in this part, B accelerates, okay, E decelerates. Even in this part, the same thing is happening. B accelerates, E decelerates. Okay. But now after this, what is happening? B starts decelerating and A starts accelerating because the spring is extended. So eventually it reaches a stage again where the spring reaches maximum extension. So when it reaches maximum extension, again they will have the common velocities, which was V2 by 2, V2 by 2, or so this common velocity was equal to that 7 by 12 V0. So maximum compression and maximum extension, the values of V are the same. Okay, just that there is a half a time period between them, from maximum compression to maximum extension. If you think of this like an SHM, so in the SHM with respect to center of mass, if this is T equal to 0, this is quarter of a time period, then this is half of the time period, and then this is 3/4 of the time period. And then at one full time period, it's back to where it started from. So here to here is a half cycle of SHM with respect to center of mass. And the center of mass is here moving with uniform B. Okay. So like that. So there are many ways of looking at this question actually. Okay. But this should be then obvious. Okay. So when you compare this state here, when you compare this and this in terms of momentum conservation and energy conservation, you don't need to look at the SHM thing at all. You just compare it that way only. So you can see in both these states, the potential energy is same. Okay. Kinetic energy is minimum. Is the same for these two. So therefore, X maximum of extension is the same thing as X maximum for compression. Is the same thing in this case as whatever we had got earlier, 0.77 centimeters. Okay. You should not have to think twice also about this. Okay, this should be pretty obvious. Okay. Now for the maximum velocity of B, that is this part I want to solve. This one. This one here should give us the maximum BB. How I'll solve. Now here is something in which our SHM method might help. Okay. Let me show you how. So if I look at the SHM of system about the center of mass, how that is happening. I am traveling along with the center of mass. Okay, so I'm now in an inertial frame. So in my frame, what is happening? A and B are doing SHM. Okay. So you'll also realize that initially at t equal to 0, A was going at a speed of v2 by 2 and B was coming at a speed of v2 by 2 like this. Okay, this was at t equal to 0. Then at quarter cycle, they reached the closest position and they came to rest with respect to center of mass. But this is in center of mass frame. Okay. So these velocities which I'm taking are with respect to center of mass. So when they came closest in the center of mass frame, then there was this two were at rest. Okay, with respect to center of mass. This is at t equal to t by 4. Okay. Then what happened? Again at 3t by 4, they came back to natural length. Okay. But this time in the center of mass frame, what is happening? This and this are having a velocity in this direction. And that velocity will be the same as this. v2 by 2 and v2 by 2. Okay. So you can see that now if I look in ground frame, because VCM is like this now. So from this third diagram, you can see this is at t equal to 3t by 4. Sorry, t by 2. So it's back to natural length. Okay. So it is in this third frame at this point of time. Okay. P has maximum velocity along positive x-axis. Okay, with respect to center of mass. Okay, so VB with respect to center of mass is equal to positive V2 by 2, which is the maximum. Okay, so that means VB with respect to ground is also maximum now. And that is equal to how much? It is this VB with respect to center of mass plus VCM. So that is a trick I can use here. So this is V2 by 2 plus VCM itself was V2 by 2. So it will be V2. Okay. That's one way I can understand it. Okay. So VB's maximum value will be equal to V2, which was, by the way, A's initial velocity. Okay. And this sound I'm now talking about in ground frame. So that was equal to that 7 by 6 V0. Okay, whatever. So that's one way of understanding it. Okay. Another way of understanding it is, another method is that when you start from this position, okay, with this going at V2, okay, then you reach maximum compression and then later at some stage you again reach natural length. So the moment you reach natural length again, what has happened is that the potential energy here is 0, the potential energy here is 0. So here to here, it is like transfer of momentum from A to B, okay, with conservation of kinetic energy. Not for the whole thing, but only from this picture to this picture. And this is potential energy, okay? Potential energy of the spring with conservation of kinetic energy for A plus B. So obviously, because they are equal masses, they will exchange velocity. No? So here VA will become 0 and VB will become equal to V2. So it was obvious. But even, for example, if the masses were different, if one was M and the other was 2M, you could just use the perfectly elastic collision formula with E equal to 1 and you would know the maximum velocity of B. Okay, hope you're understanding this point. Even if A and B had different masses, suppose this was MA, okay, and this was MB, okay, and when these guys started, this one had a velocity, whatever V, or let's say V prime. This was at natural length and this was at rest. So when it again reaches a situation where the spring is at natural length, that is when the momentum transfer from A to B has become maximum. So this is when VB will become maximum. Okay. So again, from this picture to this picture, it is a case of E equal to 1, because again, this is at natural length. Okay. So there is momentum transfer. So in a general case also, what would happen, this VB's maximum value would be the final velocity of this in a collision between these two. Okay. So in a collision between these two, the final velocity of B would come from this formula. It would be 2 times m1, so that is 2 times ma upon ma plus mb times b prime. This would be the case. यहाँ पे ma is equal to mb, so that vb max is coming equal to this b prime, which is this. So this is also a very easy way of calculating the maximum velocity of b in a situation like this. Yes, so that is correct. It will be 7 by 6 v naught, so that will be 28 only. So in this case, you can see that the final conclusion we are coming to, VB's maximum value is V2 only, which was equal to our 7 by 6 V naught, which was equal to 28 centimeters per second, which was the initial velocity of A. Okay, so hope the methods both are clear to all of you. Okay, so I'm moving on to the next question, but if you have any difficulties with this, just drop me a message. I'll help you out further. Okay, you can take down the equations for both the methods and all later from the notes I'll send you. Okay, now I'm moving on to other type of collisions, because that's also important. Okay, so let's quickly look at this situation as a practice question. So we have an inclined plane of 30 degrees. Okay, and a particle is dropped from a height of something. U is equal to 0. This height is equal to, let's say, 20 meters. G is equal to 10 meters per second square. Now, what is observed is just after the impact, this particle has a horizontal velocity. So just after impact, it has a horizontal velocity. So the particle collides, and just after impact, it has a horizontal velocity. Okay. So first of all, we have to find the coefficient of restitution, and we have to find the velocity just after impact, how much this is. Okay. So in this, we will be using the concept of collision of particle with a rigid surface. Okay, so this is a fixed rigid inclined plane. So this should be fairly easy. Yes, Ganesh, that is correct. Okay, Ganesh, can you tell me the velocity? Acha, yeah, that's correct. Okay, so we just need to apply, geometrically a little bit of conceptual things over here. Rest of things are easy. So because this is a 30-degree inclined plane, the impact velocity that the particle will have just before coming in contact with the surface, this is just before impact. The impact velocity, if I call that V naught, it will be √2gh. Okay, and that, if you work out, will come out to be 20 meters per second. But more importantly, with respect to the normal, okay, that will be at 30 degrees like this. So we can see that V naught cos 30 is the normal component, okay, of impact velocity. So it is in fact the approach velocity. Okay, so V approach is equal to 20 into whatever, √3/2. So 10 √3 meters per second. That is my V approach. Okay, and I can also see that V naught sine 30 degrees. That will be the tangential component. Okay. Now, as the impact happens, we all know that the collision impulse that acts on this guy, this will be normal. Okay, so that normal impulse kind of thing. Okay. So that means what should happen is that the collision impulse it is normal in nature. Okay. So therefore, tangential momentum should be conserved. Now you might ask, how is that case possible to conserve momentum? Because gravity is continuously acting. But here, again, the time of impact is very short. So the collision impulse is very large compared to the gravitational impulse for that time delta t. That delta t is a very short time, very short collision time. So during that time, the impulse due to gravity is negligible. Okay. So now immediately after impact, if it has a velocity v like this, which is horizontal, okay, then what we can conclude from that is that whatever that velocity v, this time this angle is 30 or this angle is 60. So just after impact, it has a horizontal velocity. So that implies that v sine 30 is basically the normal component. Okay. And the normal component is nothing but the separation velocity. So the separation velocity is equal to v sine 30 or v/2. Okay. So now when we connect this and this, we can see that the separation velocity, whatever it comes out to be, it should be E times the approach velocity. So we'll find out this value of v, but v/2 will be the unknown coefficient of restitution into 10/√3 or 10√3, whatever. Okay. So this is becoming our equation 1. This is becoming equation 1 by applying the definition of coefficient of restitution. By applying this definition, we are getting the first equation, which is this. Okay. Whereas we had seen that the tangential momentum should be conserved. So now we can see that this has a tangential component of v cos 30 degrees. Okay. So this is the tangential component. Okay. So tangential momentum conservation, this thing now will tell us that mv cos 30 should be equal to, from here, mv naught sine 30. Okay. So that tells us that v should be equal to v naught tan 30. So v should be equal to 20/√3 meters per second. And that is our second equation, or basically you can say this is the second equation. This is coming from conservation of tangential velocity or tangential momentum. And why we are able to conserve tangential momentum is because of the reason I've told you earlier, that the collision impulse is normal. So the tangential component of momentum should be conserved. Okay, so now you connect equation 1 and 2. Okay, so from equation 1, I'll get the coefficient of restitution as V by 20 root 3. So V is 20 by root 3. So as you worked out correctly, Ganesh, E is this. Okay, and the horizontal velocity just after impact we've already calculated. It's 20 by root 3 meters per second. And then typically in a question like this, you're also asked to solve the projectile motion part. So that I'm not going into, but later when you're revising, maybe you can work out that you know it will collide here, then again make a collision. So you can work out those multiple collision things all and all also. Okay. So again, this is a pretty standard type of collision. There's nothing extraordinary in this question, but it's like an average JEE Advanced type of question. So you should be able to do this pretty fast. Okay. Now in JEE Advanced, you can get a question where instead of this being horizontal, it's at 45 degrees. So you have to accordingly adjust the question. Okay. Suppose something like this is happening, that instead of the velocity after impact being given to be a horizontal, but it's given that the object falls like this. Okay, this angle is 30 degrees, and then after impact, it has a velocity which is like this, which is at 45 degrees to this. So then you accordingly adjust this. Okay. So accordingly, you'll see that the impact velocity is V0 like this. Okay, this is the normal. Okay, so you can see that in this case, the approach velocity is V0 cos 30. Okay, because this angle will be 30, and the separation velocity will be V sin 45. Okay, or cos 45, whatever. Okay, and you will see that the tangential component of this thing is V0 sin 30, and that should be equal to this velocity is tangential component, so that should be equal to V cos 45. So here your equation will become like this. Instead of horizontal, if it was given 45 degrees, then your equation will become like this, that your V0 by 2 is equal to V by root 2. That would be our first equation, and then this thing, that V by root 2 is equal to E times V0 root 3 by 2. So this would give you a different value of E and a different value of V, given that V0 was 20. But the concept is the same. So you have to just be careful about the geometry of this. Okay, very good. Nishit, you have also got the answer correctly. Bhumik, just check once, right? One thing you have to understand that like you should be aware of that in a collision, the kinetic energy cannot typically increase. Okay, it will decrease. So later today we'll see an interesting problem where translational kinetic energy tends to increase, but you'll still realize that the fact that it is inelastic means that, or even if it were elastic, the kinetic energy cannot increase. At best, it can remain the same, okay, in a collision. Anyhow, so before I come to those rotational collisions, one more important type of example. So I'm just going to take you quickly through this example so that we don't spend too much time on this. But sometimes you have a question like this, that you have a double inclined plane, okay, or an inclined plane that is connected to another incline through a corner, okay, like this. Okay. And it's given maybe that this inclined plane is at some angle alpha to the horizontal, and this angle is at some angle beta. You can see beta is greater than alpha. And then a particle is released from somewhere here, so it comes sliding down. Now, when it comes here, it makes an impact with some coefficient of restitution which is given, and then we have to find out what the velocity is after it reaches somewhere here. Let's say we have to find this final velocity, and for that, it's this kind of thing is given to us. Okay. So what you have to understand here, if this height is h1 and this height is h2, you have to understand what is happening at the corner. Okay, so I'll take the corner point as P. So at the corner point P, you are having a collision between two such surfaces. Okay, this and this. So what you have to understand is what is the angle between them. This becomes the critical thing over here. that what is the angle. Okay, just a minute. So this is this. Okay. Now in my diagram, what becomes very critical is what is the angle between the inclined planes, given that I know alpha and beta, and obviously beta is greater than alpha. So you realize that the angle between them is how much? Ganesh, I will come to your point of super elastic collisions also, but there's some kind of energy is released, like some chemical potential energy, like there'll be an explosion or an implosion or something like that. Okay. So in the mechanical type of collisions, I'm not talking about that. So I'll just come back to your point in some time. So see this angle here, this is the one I'm talking about. This angle, suppose it is theta. So you'll realize theta is how much? It is beta minus alpha, because this angle here is alpha and this whole angle here is beta. Okay, whereas this angle is alpha. No? Okay, so when the particle comes here for the first time, when it impacts at the point, corner point P, the impact velocity is along this inclined plane. See, it's along this one. Okay, so this is suppose the impact velocity. So that impact velocity is fallen from here to here. So when it reaches here, this impact velocity will be root 2 GH1. Okay, and then what will happen immediately after collision? It is now going along this inclined plane, because suppose it is given to us that the coefficient of restitution is 0. There will also be a case where E is not 0, but suppose it is given to us that coefficient of restitution is 0. Okay? So if coefficient of restitution is 0, then it should go like this just after impact. It should be along this inclined plane. So what will happen is coefficient of restitution is 0. That means at this surface, okay, now this angle is theta, the same as that angle over there. So V0 cos theta is the tangential component, so that is conserved. Okay, and V0 sin theta was the approach velocity, whereas V separation became 0. That's why my final velocity is along that inclined plane. So once I've got this, now I can see that okay, this velocity just after impact V1 will become V0 cos theta, where theta is that beta minus alpha. Okay, and then of course from here to here again I'll apply work energy. So let's say by the time it reaches here, the speed in fact becomes V2. So this is a smooth surface. The first one is also a smooth surface. So V2 square will be equal to V1 square plus 2GH2. Okay. So finally I'll get that V2 is equal to square root of V0 square cos square theta plus 2GH2. And V0 square was that much. So I'll get square root of 2G into H1 cos square theta plus H2. Okay. So this is the case where the collision is perfectly inelastic at the corner. So hope this is clear to all of you. Okay. Now on the other hand, if the collision was not perfectly elastic, then what would happen is that at this point, this came and made an impact like this. Now just immediately after impact, this velocity would become like this at some angle, let's say phi like this. Okay. So then we would have V1 sine phi. That would be the separation velocity. So that would be equal to E times this angle was theta, remember? Okay, with this inclined plane, this angle was theta. Okay. So this would be E times V0 cos theta. Sorry, V0 sin theta. Okay. Because this V0 sin theta term, this would be the approach velocity. Whereas this V1 sin phi term, okay. And of course, V1 cos phi would be equal to V0 cos theta. which is the tangential component of velocity. Okay, so then from that we would understand what kind of projectile motion it's making. Okay, so you will find some questions like this in previous year JEE question banks also. Okay, this was a question where beta and alpha was 60 and 30 respectively. A few years back, I remember, maybe 2000, I don't know, maybe 12 or 2011 or something like that. Okay, maybe even 14 or something. So you can, it was a paragraph question, so you can go through that. Okay, now I'll take you through another case of slightly more tricky version of this type of question. Okay, where one more thing is happening in this. So the inclined surface now that we're talking about, it is not going to be a fixed inclined surface. It is going to be the inclined surface of a triangular wedge. See, we have that kind of situation. Okay, so let's say this triangular wedge has this angle equal to 53 degrees and mass capital M. And now a particle of mass small m is dropped from here. It's dropped like this, okay, from a height h. Now again h I'll just for convenience take as 20 meters. That's a very convenient value. Okay. Now it is given that E is equal to 0.6, okay, and the particle has horizontal velocity just after impact. Okay, so let's say that particle's horizontal velocity is v1. Okay, and this is a smooth surface. Okay, so we want to find m by m ratio. Okay, and the value of v1 and the value of v2. Okay, that is the wedge's velocity after impact. Just try this question out, people. Ganesh, coming to your earlier point, super elastic collisions. You understood what happens in super elastic collisions. Some other form of energy is released to form kinetic energy. Like when object, suppose one particle comes and collides with a sphere or something, and as it collides, the sphere explodes, or the sphere has some kind of elastic potential energy stored in it because of surface tension or whatever, and that releases. So there is some structural change in the colliding object which releases some kind of potential energy, whether it is elastic energy or chemical potential energy or anything like that. And that results in the kinetic energy of the system increasing, right? Exactly, Ganesh. Okay, otherwise kinetic energy cannot increase on its own like that. So, I mean, I could give you like a very simple example of that. That suppose I have this situation that I have a block like this, and I have a spring attached to the block, but also attached to the spring is a thread. There's a plate attached to the spring and a thread is attached to that, which is keeping the spring in a compressed state right now. So this is at L minus X naught. Okay. And this system is at rest. Now another block comes and collides with this. Okay. And either as a result of the collision or by some other mechanism, when the collision occurs, I break the thread. So this elastic potential energy will eventually get released as extra kinetic energy for the system. So the final kinetic energy after the spring disengages the two blocks will be more than the initial kinetic energy of this, because the total energy of A plus B will be conserved. And initially A did not have kinetic energy, but A had potential energy because the spring is attached to it. So this could be an example of a mechanical version of that super collision you're talking about. Okay. Okay, but Nishit, the thing is, see, that M by M ratio now you have to give me as a numerical value. It will not come in terms of V1 and all. Acha, V1 you have taken as root 2 J's, is it? So first of all, tell me, can we apply any kind of momentum conservation here? Will we be able to apply any kind of momentum conservation in this problem? Okay. Yeah. So Nishit, you are correct that the ground applies horizontal impulse, but sorry, ground applies impulse. That's very correct. But that impulse is in which direction? Vertical direction. So as Ganesh, you have said the horizontal momentum is conserved, but for what? For the whole system, na? For the particle plus the triangular wedge. Right. So one thing I can do is I can conserve horizontal momentum for the whole system. That is the particle plus the wedge. Now I'll just give you a hint. There is another conservation of momentum that we can do. Okay. Another type of conservation of momentum that we can do. Think carefully. Yes, so that's correct. So momentum along the inclined plane of the wedge, but for what? For the particle. Okay, very good. So that's what we'll do. So now I'm going to concentrate on the impulse picture, including the collision impulse as well as the ground impulse. If you look at that. So at the moment when the particle comes and hits this, okay, so I'll just treat this like a tiny sphere to make life a little easier. Okay. So the impact impulse between the two of them, that will be in the normal direction. So I'm just drawing the impulse picture. Okay. I'll come to the momentum and all later. Okay. Should actually be along the same line, but anyway. So this is the collision impulse. This is the normal impulse which is acting between the two of them because of the collision. Okay. But along with this, this has a vertical component. So the ground doesn't allow this one to move. So the ground applies another normal impulse. Okay. On the wedge. Okay. So now based on this, if we look at, now I'm just drawing a miniature diagram here. Just before impact, this had a downward velocity, let's say V0, and that V0 was √2 GH, which was our favorite value of 20. Okay. And just after impact, okay, this guy has a horizontal velocity, let's say V1, and this guy has a horizontal velocity V2. Okay. So what should happen when I look at this diagram? Okay, you can see that this is internal for the system. Okay, whereas this one is external. So this is coming from the ground. So for the system, we can conserve the horizontal momentum. So for the system, that is particle plus wedge, we will apply conservation of horizontal linear momentum. Okay, so 0 before the impact, you can see in this. Okay, and that is equal to capital MV2 minus small m. So V1 is to V2 is equal to capital M is to small m. Okay. So you can even do like this, that suppose we take m by m. Sorry, we take small m by capital M, which we wanted to calculate as x. So we have the first equation that V1 by V2 is equal to 1 by x. That's the first equation. Okay. Now next we look at the impulse picture on the particle. That will give us something very interesting. Okay. The impulse on the particle, the impulse is normal to the inclined surface, which is at 53 degrees. Okay, so that means its tangential component of momentum should be conserved. Okay, so for the particle before impact, this velocity was V0. Okay, and this angle was theta. So tangential component was V0 sine 53. So that is 20 into 4 by 5. So 16 meters per second. Okay. After impact, the particle has a horizontal velocity of E1, which I've taken like this. Okay. So that is at an angle of theta like this. Okay. So tangential component is V1 cos 53. So that is 3 by 5 V1. So So we have V0 into 4 by 5 should be equal to V1 into 3 by 5. So interestingly, it not only changes direction, but the particle speeds up. Its kinetic energy increases, which tells us that probably this is a heavier object. The wedge is probably going to be heavier. Let's see what comes out. So in this case, V1 comes out to be 4 by 3 of 16 meters per second. Okay. So now you connect that with equation number 1. Okay. And that will give you the value of V1 in this. So now we have two unknowns, V2 and X. So we need one more equation. Okay. Then we can treat it like now variables and equations. So we have V1, V2 and X, three variables. So we have calculated V1 through equation number 2, but we need a third equation because we have three variables, V1, V2 and X. So now what is the connecting equation? The coefficient of restitution one. I have to make use of that. Remember, coefficient of restitution was given to me. It was 0.6 if I remember correctly. Okay, so I have this now. Now coefficient of restitution equation. Let's see how we'll make use of that. So before the impact, we had a situation like this, that the particle came and hit the block with a velocity like this. So V0 cos theta is the normal component. So that is equal to the approach velocity. Okay. And after the impact, we had a situation that this one has a velocity V2 and this one has a horizontal velocity V1. So to calculate separation velocity, we can do one easy thing here. We can get into the frame of the wedge. So in that frame, the particle has a relative velocity of V1 plus V2. Okay. And that relative velocity has a component along the normal direction of how much? Sine theta. Okay. So V1 plus V2 sine theta is the relative velocity sine theta component, which will become the V separation. Okay. So V1 plus V2 into 4 by 5 is equal to V separation. Okay. Whereas V0 into 3 by 5 is equal to V approach. And earlier from this, so first let's connect these two. So V separation should be equal to E times V approach. So 4/5 V1 plus V2 should be equal to 0.6 times 3/5 V0. Okay. And then from equation, so this is becoming our third equation. Now we'll just carry these equations from before. V1 was coming out to be 4/3 V0. Okay. And we had V2 was equal to V1 x times V1. Okay. So we'll substitute this information here and hopefully that should give us what we're looking for. So 4/5 V1 plus x V1 should be equal to 1.8/5 V0. Okay. So this, okay, and then 4/3 V0 into 1 plus x from here. Yes, so that should give us 1.8/4 V0. So 1 plus x should become 1.8 into 3/16. So that is giving me some impossible situation for x now. Anyhow, so that means that, for this kind of collision, that horizontal velocity is not possible for this one. Let's see if we can change some values and get that. But if I change theta to 37 degrees, okay, instead of 53, and I change the coefficient of restitution to, let's say, 1, I might be able to get a value. So this is showing me that x should be negative. So it is not possible actually. What it is showing me is that a coefficient of restitution 0.6 collision cannot result in a horizontal velocity after impact for this one. Okay, but I'm just saying that suppose we had this equation where this triangular wedge had this angle as something different, like let's say it had 37 degrees, and the particle after it made the impact, it went horizontally, but the coefficient of restitution was 1. Then our equation 1 would have been the same, that mv1 is equal to capital mv2. So v2 is equal to x times v1, where x is that ratio that we're looking for, m/m. Okay. Then our equation 2, which is which was coming from the tangential velocity conservation, would have given us that v0, what would it have been? V0 sine 37 would have been equal to v1 cos 37. So we would have got v1 as 3/4 v0. So that would have been our second equation. Okay. And the third thing, of the coefficient of restitution being 1, the separation velocity would have been equal to the approach velocity. So the separation velocity would have been v relative, because in this frame, this v relative would have been in this direction. Okay. This angle is theta. So v relative sine 37 would have been equal to v approach. Okay. And now v approach would have been how much? It would have been equal to v0 cos 37. So this equation would have given us that V1 plus V2 into 3 by 5 would have been V0 into 4 by 5. Okay, so this would have been our third equation. So we have V1 plus V2 is equal to 4 by 3 V0. Okay, then we substitute this. So V1 into 1 plus X is equal to 4 by 3 V0. Okay, and then we substitute this. So 3 by 4 V0 into 1 plus X is equal to 4 by 3 V0. So we will get 1 plus X is equal to 16 by 9. So thankfully this is giving me a possible value of X, which is how much now? 7 by 9, is it? So that means M is to M, but V is to 7 is to 9. Okay. So you can just see that it is impossible for that case where the angle was 53 and the coefficient of restitution was 0.6, but it is possible for this case. Okay, and it might be possible for E less than 1 also, but you'll have to take some pretty large value like 0.9 or 0.8 or something. If you take something relatively smaller like 0.6 or 0.5, again you might not get a logical answer, which means that it's not possible that the velocity will become horizontal after impact, right? So hope this concept is clear to all of you people. Okay, now I'll move on to some of the doubt questions. Okay, Bhumik, I'll first understand your doubt, just a minute. Okay, so Nishit and Ganesh, you got the value of X negative for the first partner, so you understood the significance of that. It means that, you know, that type of collision cannot result in the velocity of the smaller particle being horizontal. In that type of collision, what you will see, now you can do a counter example where you take some ratio of mass, like take 1:1 ratio only, and take E is equal to 0.5 or 0.6 or something. You'll see after impact, this particle will have a velocity like this. It will go into some velocity like this instead of having a horizontal velocity, whereas this will go like this. It just cannot have a horizontal velocity. That's the meaning of it. Okay, Nishit, so hope that point is clear to you also. Yes, yes, it can be done that. Okay. Okay, now, Bhumik, I'm coming to your point. So Bhumik is asking that why can't we conserve in the line of impact as we did for the, yeah, why can't we conserve in the line of impact as in we did for the two block collision? Even collision impulse acts in that situation. So difference is, you know, like if I have a situation like this, that suppose I have, like, you know, this triangular wedge and this particle, they are colliding in free space. Suppose this is gravity free space, or even that, you know, these two are shapes on a horizontal smooth surface, so their weights are balanced by normal reaction coming out of the plane. Okay, so in that case, what would happen? Just after impact or during impact, this is the only impulse that would act, this and this. So for this system, the net impulse would be 0. So that is why the momentum of the system would be conserved. Understood the moving? Okay. Whereas here, what is happening? This wedge is actually lying on the ground now. So the ground doesn't allow, and in this case, what would happen after the impact? After the impact, the particle would have maybe gone off in some direction like this, because its initial momentum was in this direction. Its impulse was in this direction, so its final momentum is in some direction like this. But the wedge would have definitely gone off in this direction. The wedge would have a velocity v2 like this. The particle would have some v1 like this. No, the wedge's direction of velocity would be along the impulse. You understanding now, Bhumik, the difference? Okay, good. Whereas here, this cannot happen because along with this normal impulse, there is also the normal impulse that the ground is applying. Apart from the collision impulse, there is also the normal impulse that the ground is applying. So that means on this whole system, net impulse is not zero. Okay. J prime is the net impulse. Okay, but it is vertical, so we are able to conserve horizontal momentum. Okay, right now I'm coming to some of the doubt questions next. Okay, so I will just give me a second. I will put up one question. The screen. I want to start with this one today. Okay. Yeah, so people just go through this question for a moment. Okay, then we'll discuss about this. Okay, so read very carefully. You have two coaxial solenoids and the current in them is varying with time with a particular thing. Then I'll give you a hint about what is happening here. Okay. Okay, so yeah, Ganesh. Okay, so the thing is, now we will consider this as the perfect solenoid, na Ganesh. So just outside the solenoid, the magnetic field is zero. We will treat them as like ideal solenoids, so they are very long and tightly wound. So the solenoid's own structure is something like this. So it has that idealized kind of field, that inside the field is almost uniform. Only slight variation as you come near the corners. And this field is actually going to infinity and then coming back, it's going like this, taking a very long route like this. So here the magnetic field is zero. Here the magnetic field is zero. So the moment we are taking tightly wound solenoid, now we have to assume like this. Is that clear, that part of your doubt, Ganesh? So we will see that in this type of a region, there is, let us say, magnetic field B1, clockwise currents are going into the plane. But in this type of a region, there's a magnetic field B2. So B2 will be like the field because of both the solenoids combined, superposition of two fields. Whereas B1 in this region will be the field only because of the outer solenoid. Okay, so B1 will be mu naught Ni. Because on the outer solenoid, there is a current I. In this diagram, I've shown only one solenoid, but yes, okay, like that, okay. Whereas if I was concerned with the field inside, which I'm not in this case, but that would have been mu naught, like both have the same number of windings, right? Have the same number of turns per unit length, N. Okay. So mu naught N I plus 2y. Okay. Now this I is equal to what? It is some KT, na? Okay, like this. K into time. So the part that is in concern for us, that B1, okay. Actually, B2 will also come into picture when we look at the electric field, because the flux will be affected by B2 as well as by B1. So this is a very interesting problem in that sense. Okay. So anyway, so B2 is equal to 3 times mu naught N into K into T, like this. Whereas B1 is equal to mu naught N into K into T, because I is given by K. Okay. So now to understand the electric field in this region, which is of a radius, what is this radius now? Small r or something. Okay. So as a result of the increasing current, a charged particle initially at rest between the solenoids. So we'll take it as R1 plus R2 by 2 or 3R by 2 starts moving in circular trajectory. Okay, so this small r. So when we take this circular path and we do the path integration for this, integration of E dot dl should be equal to rate of change of magnetic flux. So we will get on this side E into 2 pi r. Okay, that should be equal to rate of change of B2 into pi r square. Okay, plus B1 into pi r square minus capital R square. Okay, Ganesh, this is making sense, this equation now? So this particle, the flux going into the plane is increasing, so the direction of the electric field will be coming out. You know, clockwise is increasing. So the electric field at every point will be tangential like this. We have that non-conservative, non-electrostatic electric field. Okay, so this E is non-conservative, okay, non-electrostatic induced electric field. So actually we should not even call it an electrostatic field, it's an electric field just. Okay. So that is given by this. So this E into 2 pi r should be equal to, now we can take a lot of things common. We can take mu naught n k pi common. Okay. And from this B2 term, we will have 3 r square. Okay. That thing will cancel, or we can just write like this also. D by dt of this whole thing. So then we'll keep the t. Okay. And this term will have mu naught n k I have taken common outside, pi I have taken common outside. So I have r square minus capital R square t. Or something like this. Okay. So mu naught n k pi into d by dt of 3r square minus r square. So that's 2r square plus r square t. Okay. So now you must have understood what is happening. If the particle remains in circular path, that means the charge of the particle into electric field at any instant of time is equal to the tangential force acting on it. Okay. So there is tangential force means that there's tangential acceleration. So it's in a non-uniform circular motion. Whereas at the same time, because of V, there will be a magnetic force acting, you will see in the inward direction, QV cross B, because Q is positive, we'll assume, or if Q is negative, then the direction of velocity gets reversed because electric field is, electrostatic force is opposite to E. So V cross B will be radially outwards, but negatively charged particle. So either way, the particle will experience centripetal direction of force because of magnetic field. Okay, so now in that non-uniform circular motion, you have to take care of that point, that at any instant, the instantaneous value of centripetal force should be equal to QVB. And the instantaneous value of tangential force, which will be a constant force over here, will be equal to electrostatic force. That will be equal to mass into tangential acceleration. Okay, very good, Ganesh. So I think it should be clear how to do this question. So I'll just quickly wind up this part, show the calculation to everybody. Okay. So this E into 2 pi r is like this. Okay. So from this, we will get the value of E. Okay, and that will be independent of time. Okay, because you can see d by dt of this term, it's independent of time. Okay, so now I can see that on the particle at any instant, if I have a particle of plus q, then q into E is the tangential force. Okay, and at a particular instant of time, if it has gained a velocity v, then there is magnetic force acting on it in this direction. Okay, so magnetic force, which is qvb, should be equal to mv square by r. And this v will be equal to tangential acceleration into time, because it started from rest. Okay, and that tangential acceleration will be qe divided by m. Okay, because the electrostatic force is, I mean, the electric field is constant in time. Okay. So I'll connect this with this and I'll get the required relation. Okay, so hope this is clear to all of you. Okay, I'm just going to move on to another question. Just give me a moment. Okay, so just go through this question next. We will discuss. So this question I think is sent by Samik. Okay, so let's go through this question carefully. Yes, Bhumik, I will send the recording now of today's lecture also. Achha, I think previous lecture I've forgotten to post now. I will send it on YouTube also. The previous lecture also. I mean, I will upload it on YouTube and I'll send you the notes also. Yeah, Nishit, let's understand that only. Okay. So what is happening? We have this metallic pulley, okay, which is in the shape of a disc and all that. So it's a solid disc of radius A. So we'll take moment of inertia of the pulley obviously as ma square by 2. It can rotate freely about the horizontal axis, passing moment of inertia. Achha, that is only given to us as I. Okay. Light string is tightly wrapped around one end connected to the block. The center of the pulley and its circumference are connected by a resistance like this. Okay. The contact of the resistance at the circumference does not cause any friction. Okay. So hope you understood this point, that over here, now, between this point and this point at connection over here, there's no friction. This like maybe there's a carbon brush which is just against that metallic disc, and it hardly applies any friction, though it maintains electrical contact. It does not create any friction. That is the meaning of this, that there's no friction at the contact point. Okay. And uniform magnetic field and all that. Okay. So basically this is motion generated EMF. So you know that when you have a disc like this, when you have a metallic disc like this, which is rotating in a magnetic field which is uniform like this, okay, then that creates that rotation of the disk. It creates a potential difference. So suppose omega is like this. Now in this, omega will be in opposite direction, but if omega is like this, then it is equivalent to if you had a rod of length L which was rotating about this at omega in a magnetic field like this. And the trick to remember is that this end of the rod has a velocity of L omega, and this end of the rod has a velocity of 0. So the average velocity is L omega by 2. So the EMF induced is equal to BL into average velocity. So that's one very easy way of remembering. It is BL square omega by 2. Now this thing, now the disk actually acts like a equivalent rod of this thing, it acts like a equivalent, many rods like this in combination. So there are, so this, I mean, between the center of the disk, let's say, which is C, and any point on the circumference, which is, let's say, P, there is now this potential difference. Any point on the circumference, whether it is P1, P2, or P3, whatever. So it will have, like in this case, it would, the EMF induced would have been in what sense? V cross B is pointing towards the center. So the EMF induced would be like this. So in this case also, the EMF induced would be such that the center would be at higher potential. So VC minus VP1 or P2 or whichever point we take, the center and any point on the circumference, they would have a potential difference of B omega L square by 2, where L is the radius. Right, this point is clear, Samik and others? Right, I think this part is standard, na? Disk mein kaisa hota hai, na? The next part is the tricky part, the current generation. Okay, so anyway, so if you, now I'm switching to my whiteboard because I need a bit more space. Just a moment. So now if we look at the disk now, we can understand that it has like remember in motion generated EMF, what actually happens is there is induced charge. That is what creates motion generated EMF. Okay, so in this case, at some instant, if this is rotating at omega like this inside a magnetic field B like this, So you can see that the redistribution of charge will be in which sort of direction. Okay. Here V cross B will be in which direction? B at any point on the disk like this will be like this. So V cross B will be outwards now. So there will be positive charge which redistributes on the outer surface. Maximum linear charge density on the circumference. Okay. So there is a like a charge gradient, like the potential gradient because of redistribution of charge. So there's like this, then little less charge here, okay, then little less charge here, then eventually there's some negative charge, okay, very high density of negative charge near the center. Okay, so there are basically there are radial electric field lines which are formed. So the internal electric field is forming radial lines like this. So I think Samik, now you understood what is happening. Huh? So now this is like a resistor for which the center is 1 point and the entire circumference is one common point. So the potential difference between the center and the point P is the induced EMF, which is B omega L square by 2, or L is equal to the radius. So in this case, I think it was A or whatever. Okay. So now how much will be the current? Achha, we are considering the disk as without resistance. No? So the current induced in the disk, or the current going through this part, this is actually not in contact with the disk, this part of the wire between C and here. Okay, that's not in contact. Only at C it is in contact like that. So this will have a current in which direction? It will have a current in this direction. Okay, and that current now is actually coming out like this. Now inside, like this is the source of EMF now. So inside a battery, the current flows, the internal current inside the battery flows from the negative to positive terminal. That's why the external current flows from positive to negative. So this is how that current is flowing. Okay, and that total current is B omega L square or A square divided by 2R whatever. Okay. So now you have these radial lines of current, and on those radial lines of current, what will happen? Magnetic force will be acting, ideal cross B, like that. So they will be generating an anti-torque. So there will be a torque because of magnetic effect like this. Okay. So going back to our free body diagram of the situation, this whole rotating disk and all this. Okay. So some tension here and some magnetic torque here. Okay. So that will ensure that this has some angular acceleration alpha, and this has some linear acceleration. So if this mass is m, so for the block you have mg minus t is equal to ma. For the disk or the pulley, you have t into radius. Radius I have taken as L. Okay. In the problem it is given as small a. So minus torque due to magnetism, because that torque is always opposing, is equal to I alpha, and E is equal to R alpha, or in this case I take it as L alpha, so that I don't confuse it with resistance. Okay. So I am taking L for the radius again because I don't want to confuse with acceleration A. So these are my three equations. Okay. So when you solve these three equations, again you will get that type of acceleration. That acceleration will be some alpha minus beta into V, that kind of thing. So your V will become some terminal velocity into 1 minus e raised power minus t by tau kind of equation. Now the only thing is, how do we calculate this torque? So that is where that distribution of current radially, we'll have to take that into account. So I'm coming to that, but hope the conceptual part is clear. So at any radial point, now you can calculate current in various ways. Actually, you can use Ohm's law. Now you can take you can slice the disk into rings, and you can take the current going through that ring, and that way also you can calculate the ideal vector at a given point. Okay, so what's happening here is, now think of the disk like this, from the cross-sectional point of view. So if this thickness of the disk is some small d, okay, now slice it into rings like this. Okay, so that ring that I'm talking about, it is like, it's got two thicknesses. One is this, if this is r, then this thickness dr, and the other is this thickness, which is the small d, the small d like this. Okay, so the total current going through this ring is that I only. Now clear, Nishit and Aditya? So this I is equal to BL square omega by 2R. Okay. So that total current is like this. Okay. So now on this, if you consider a small element, so again I'm taking the top view. So here if I consider a small current element IDL like this. Okay. So this current element is actually equal to how much? It is I divided by this inner surface area. So this inner surface area will be 2 pi r into the thickness d into, now I'm considering a small section like this, d theta, so into r d theta. So that is the amount of current going through a small element like this over here of thickness r d theta. Okay. And plus it is going through a length where dl is actually dr, because that is the thickness of this. So this is your current element IDL, that kind of thing is this. So that will experience a tangential force, magnetic force of how much? IDL into B. So that is I into capital R, actually I've taken as L. So L d theta divided by 2 pi R d, okay, into dr. So that's IDL into B, where B is that magnetic field. Okay. So this is the magnetic force just acting on a sectional element like this, df. So that is creating how much torque? That is creating a torque of that sectional magnetic force multiplied by R, momentum. Okay. So now you integrate this to calculate the torque because of the ring. It's like a double integration problem actually. So that will give you the torque on the ring, and then you integrate for all the rings, that will give you the net torque because of magnetic field. Okay, Nishit and Aditya, is the concept clear of this question? Okay, so it's a double integration problem actually. No? You will have to take the rings, having a thickness, I mean, you'll have to take an element on the ring having this thickness equal to r d theta and this thickness equal to dr. And first calculate the torque because of the force that is acting on this element. That is the df which I've written. But that df is proportional to dr into d theta. Then you integrate across theta. So you'll get something into dr. That is the torque acting just because of the ring. And then you integrate with respect to r from small r equal to 0 to L. So that will give you the net magnetic torque. And that net magnetic torque now you put in this equation. It's proportional to omega, and omega is proportional to V. V is equal to r omega. So you will get that relation which I was telling you, that V will be equal to some tangential velocity into this type of term. Okay. So can you guys give this a shot? I will work it out in detail and send the solution to you people. Why can't we consider it as a rod now? Because Nishit, one thing you should understand now, we cannot cover the area of a disk by considering rods. Now, we'll have to consider sectors actually. You're understanding my point? If you cut a disk like this now, we'll have to consider them as small triangles. We cannot consider them as small rods. Like if you just consider how we do area of a disk by integration, no? Surface integration करके area of disk हम कैसे निकालते हैं? We cannot cut it into rods and do. We can cut it into small triangles, okay, and use that d theta angle of the triangle, area of the triangle से भी कर सकते हैं, or we can slice it into rings. So that is why here it is more beneficial to take the geometry as differential rings, okay, than sectors. Okay, so hope this is clear, people. Okay, Aditya, can you turn your microphone on? Want to discuss with you the difficulty that you have?
Yes, sir.
Nishit, yes, I will keep some time with you also later. Okay, so we can discuss. Okay. Yeah, Aditya, tell me what is the difficulty you are having, beta? Time
So
taken.
actually, I take a lot of time in understanding what the question is asking and to solve it basically. So even in the mock
any
papers.
Specific chapters? Any specific chapters where this is happening more, like in electrostatics type of things or mechanics type of things, or what?
Mostly it's mechanics. That takes a lot of time, but it's more of like the level of questions, advanced type of questions. I take generally more time. So even in mock tests, I am only able to attempt like half the section of physics.
Okay. Half the section you are attempting in how much time? Like 1 hour or more than 1 hour?
So 1 hour.
1 hour, na? So see, depending on whether physics is your strong subject or maths is your strong subject or whatever. But let's take an average situation. Suppose PCM, all three were equally strong for you. Even in that case, now advanced paper is designed in such a way that you cannot attempt all the questions in 1 hour. So let us say that you have the ability to do like let's say 80% of the questions, okay? Because obviously some questions will be beyond your range in an advanced paper. Mains में ऐसा नहीं होगा because mains are more or less even type of questions, but advanced will have some questions which are very tricky. You understanding my point, Aditya?
Yes, sir.
तो जो 80% questions तेरे range में है ना, so first of all, the thing is you have to be very sharp in selecting those questions. Like when you read the question or when you're going through the paper, na, you realize that, okay, this is a question from EMI, which is like having some double integral. So this is beyond my range. Or that is a question, let's say from, mechanics with Coriolis force or something, which I haven't heard of. So okay, this is beyond my range. Okay. So one is you have to gauge that given question is within your range or not. So you should attempt it or not. That's the first point. Okay.
Yes, sir.
The second thing is the 80% of questions that you can attempt now, they should like you should be able to attempt them within like let's say if not 1 hour, then 1 hour and 10 minutes or 1 hour and 15 minutes. So the question is where you will get the extra time from, because physics is more lengthy compared to chemistry.
Yes, sir.
You understanding my point? So थोड़ा तो trade off करना पड़ेगा कि तेरे को physics में अगर 80% questions attempt करना है, that means कहीं और से तेरे को और time निकालना है physics के लिए. अदरवाइज तू 80% आता था तेरे को, लेकिन तू अटेम्प्ट नहीं कर पाएगा. तू अटेम्प्ट कर पाएगा सिर्फ 65%.
हाँ सर. So मतलब केमिस्ट्री हो जाता है about 40-50 मिनट्स में.
हाँ, तो केमिस्ट्री हो. So rest of the time ना you distribute between maths and physics depending on which you are finding easier during the exam.
Okay, sir.
ठीक है. But yes, you have to increase the number of questions you are attempting. Like right now, if you are attempting 50%, then in 1 hour you have to increase it to about at least 70%.
Yes, sir.
So for that, one of the things you can do is like sometimes it happens that if you do a few subjective questions without doing time constraint, just for practice, then it improves your ability for understanding those complicated objective questions.
Oh, okay, sir.
So you don't have a whole lot of time. तो ऐसा नहीं है कि बैठ के मतलब पूरा Erodo solve करना or something, you don't have that much time. But every week now you keep aside like let's say 2 days in the week, and in those 2 days you keep aside some good time of 3 hours or so for doing subjective questions from the core chapters of physics like magnetism, electrostatics, rotational
Yes,
mechanics,
sir, I do
system
that
of
from
particles.
Erodo only. Every
हाँ,
week, 2 days.
Erodo से कर सकता है, DC पांडे से कर सकता है ना? So
Sir.
those type of questions ना, in like while doing the questions, don't worry about the time taken because they're subjective questions. Okay, but do the questions in depth. So that will automatically improve your comprehension of the questions when they're objective questions. You'll be able to comprehend what the question is asking, what is the situation faster.
Yes, sir.
ठीक है ना? और एक तो है देख, you have to like your maximum chance of getting a question in JEE is when you are familiar with the type of question. Obviously, repeat question तो नहीं आएगा, but it is when you are able to connect because you're familiar with it. Like whether it is like in magnetism, it can be the moment you read the question, you realize that it's cycloidal motion, or you realize it's helical motion, or you realize it's a case of a disk rotating in a magnetic field. So there has to be that radial kind of electric field. So these kind of things now you have to be familiar with. So again, that subjective questions doing that helps you in that because it creates those patterns that okay, in this type of situation this is happening, in that type of situation something else is happening. ठीक है?
Okay, sir.
तो थोड़ा systematically if you do the subjective questions ना, you can even use HC Verma for subjective questions, but do the last 5-10 questions of each chapter.
Okay, sir.
Last 10 questions also you can do of each chapter.
Okay, sir.
The only chapter where HC Verma falls short is in rotational mechanics. Rest of the things HC Verma more or less has enough subjective questions. Okay, in rotational mechanics HC Verma has far too few questions. Otherwise, like EMI, magnetism, then even chapters like collision, center of mass, they have enough questions. So even that will help you. Okay,
Okay, sir.
okay.
Thank you, sir.
Nishit, okay, beta. Nishit and Aditya, I'll go through both of your doubts because I didn't get a chance today in WhatsApp. I'll send you some hints, and if required, like I'll discuss with you. No?
Okay, sir. Thank you, sir.
Okay, people. Good night. Take care then.